Then we have electron affinity, which kind of seems like the opposite of ionization energy. Electron affinity is adding an electron to an atom instead of taking it away. So electron affinity is defined as the energy change. That's not specifying if it's positive or negative. The energy change when a neutral atom gains an electron. So we can take this neutral atom plus one electron, gives us a -1 ion plus EA. Electron affinity, that could be positive or negative. The electron affinity is usually negative, exothermic, but it can be positive. Some alkaline metals, earth metals, and all the noble gases have positive ionization energies. Is a noble gas going to be happy about getting an extra electron? No. The noble gas is like perfect the way it is, and it really doesn't want to get messed up. It's not going to gain electrons or lose electrons. It's just going to be happy in itself. How about the alkaline earth metals? Is that going to be happy about gaining an electron? That's going the opposite way of what it wants, right? If it loses, these have one valence electron. If they can get rid of that one valence electron, then they have the noble gas electron configuration and they're all good. So putting an extra one on is not going to be cool. Now the trends in electron affinity are less regular than the other trends. In fact, I would really hesitate to say that they're much of a trend at all. We see that electron affinity decreases, meaning it becomes more positive as you go down the group 1A alkali metals. So it works for that one group. There's not really a trend in the other groups. And electron affinity generally increases, it becomes more negative across a period. But again, there's a lot of exceptions there. 5A is lower than expected because that electron that we're adding has to pair up. That's the discrepancy we saw between oxygen and nitrogen when we were removing an electron. Groups 2A and 8A have very low electron affinities because when you're adding that electron, it has to go into a higher level. And the highest EA in any period is going to be for a halogen. So highest meaning it's the happiest about getting an electron. Because halogens like to form -1 ions, right? So electron affinity is, and here we have the positive negative thing again. Higher electron affinity is a more negative number. So it releases energy when you give it an electron. A positive electron affinity means you're paying to place this electron there. Here's the partial table of electron affinities. For these guys, we're just saying greater than 0. Not happy about getting electrons. In fact, I don't know if we've even been really able to measure it very well, so we just don't even really think about those guys. Here we've got large negative ionization energies, electron affinities, and these guys are quite small, so they're more positive, so less favorable. It's in the book, I have to tell you about it. Okay, properties of metals and nonmetals. You should have heard this before, but just go over this quickly. The nonmetals being not metals, a lot of their properties are like opposite of the metals. So the metals, malleable and ductile. Malleable means you can hammer it into a sheet. When you hammer on a piece of metal, it doesn't shatter into little pieces like glass does. It dents, right? That's being malleable. Ductile means you can pull it into a wire. Nonmetals, not so much. They're brittle in the solid state. They will shatter for the most part. Metals are shiny, lustrous. They'll reflect light. Nonmetals don't do that. Metals conduct heat and electricity. Nonmetals don't. Metals form basic oxides and ionic compounds. Nonmetals form acidic oxides and molecular compounds. Metals form cations in solution. Nonmetals form anions and polyatomic anions. Metals lose electrons, they become oxidized. Nonmetals gain electrons, they become reduced. So the nonmetal properties are pretty much the opposite of the metals. So we can talk about metallic character. So how closely an element's properties match the ideal properties of a metal. So metallic character increases left to right. Sorry, it decreases. Metallic character decreases left to right as we go across the period, and it increases as you go down the column. So this actually is pretty easy in my book. What is my book? So here's that stair-step line in the periodic table, right? These are the metals. These are the nonmetals. So as I go across, I'm going from the metals through a semi-metal into a nonmetal. Who has more metallic character, a metal or a nonmetal? A metal. So metallic character is higher over here and gets smaller as we go this way. And if I start up here with a nonmetal and go down, I'm going through some semi-metals into the metals. Down here I have larger metallic character. So some metals are more metal-like than other metals. And we can apply this to like gender stereotypes among people, right? People have a range of properties or characteristics. Let's just pick on guys. So, you might look at a guy and say, okay, well, he's like super masculine, right? Not necessarily better, but just more stereotypically masculine. You might see another guy and he's like, well, he has some softer qualities, not quite as masculine, might make a better friend, right? Might be better in social relationships, but just not as stereotypically masculine. The same with women. Some are girly girls, and others, jeans and t-shirts, right? So does that mean that it's not a metal? No, it's still a metal, even if it's not very metallic, right? Does this mean that chlorine is a metal compared to a noble gas? No, it's just more like a metal than the noble gas is. Okay, so that's trend in metallic character. Oh, yeah, there's another one. So this one actually has the stair-step line built in there, and there's the trend. Metallic character decreases that way and increases going down. On the basis of periodic trends, choose the more metallic element. So germanium or tin. Here we have germanium, it's here, Ge, and tin. Who's more metallic? Tin. Germanium is actually a semi-metal, and tin is a metal. How about gallium or tin? There's gallium and tin. That one's iffy, huh? Because metallic character decreases as we go across, and it increases as we go down. And so here we have opposing trends again. So it does say if possible, so we could say not possible. If I had to choose, I'd choose tin as the more metallic. Phosphorus or bismuth. Where did bismuth go? Oh, there it is. So, I don't know how many are in there, but there's phosphorus and bismuth is down here somewhere. Which is more metallic? Bismuth is a metal, phosphorus is a nonmetal, right? Boron or nitrogen? Boron's here, nitrogen's there. Boron. Okay?